All right, so there's an application of this electromagnetic induction that's really important for medical people. So it's kind of long, but here we go. It's about an MRI scan. A patient undergoing an MRI scan lies in an apparatus containing two magnetic fields, a large constant field, B, and a small sinusoidally varying field, B, as a function of time. Normally, the scan requires the patient to lie motionless for a long time. Any patient unable to lie motionless, such as a child, is sedated. Because sedation, especially a general anesthetic, can be dangerous, a sedated patient must be carefully monitored, usually with a pulse oximeter, a device that measures the oxygen level in the patient's blood. This device includes a probe attached to one of the patient's fingers and a cable running from the probe to a monitor located outside the MRI apparatus. So MRI scans should be perfectly harmless to a patient. In a few cases, however, disregard of Faraday's law of induction led to a sedated patient receiving severe burns. In those cases, the oximeter cable was allowed to touch the patient's arm. So there's the finger, if you can see it. That's the cable. And then here it touches the patient's arm, then it goes to the equipment. The cable and the lower part of the arm thus formed a closed loop through which the varying magnetic field produced a varying flux. This flux variation induced an EMF around the loop, right? Faraday's law. Although the cable insulation and the skin both had high electrical resistance, the induced EMF was large enough to drive a significant current around this loop. As with any other circuit in which there is resistance, the current transferred energy to thermal energy at the points of resistance. In this way, the finger and the skin where the cable touched the lower arm were burned. MRI staff are now trained to keep any monitor cable from touching a patient at more than one point. So years ago, I don't know, maybe 15 years ago, I actually used the same slide, and there was a student in the class who used to live near me in Laie, who raised his hand and said, "This happened to me, this happened to me." And so there you go, right? Faraday's law, closed loop, changing flux, EMF, current, burn. So there you go. Pretty interesting. Okay, let's just review what we learned in this chapter. So this was about induction and a little bit about electromagnetic waves. We learned the circumstances under which changing magnetic fields lead to induced currents. So we did two situations. We had a coil of wire and we moved the magnet, or you could keep the magnet stationary and move the wire. Then we also did that motional EMF where you just move a wire past a circuit. The motional EMF. Okay, we understand how now we understand how the motion of a conductor through a magnetic field leads to a motional EMF. We learned about Lenz's law, Faraday's law, so we know the direction and magnitude of currents, induced currents. We talked about how induced E fields and B fields lead to electromagnetic waves. Then we learned a little bit about the photon model and about the electromagnetic spectrum. And we talked about a little bit about the types of waves, how they're polarized. Okay, so let's just review sort of quickly. So this is the first demonstration that I did to show you how you can produce electricity just by changing the magnetic flux. This is the second one where you move this rail or wire, whatnot, and you're changing magnetic flux. Okay, so then we learned about Lenz's law. Whenever you change the magnetic flux, you get an EMF. If it's a conductor, you get a current. A current produces a B field. The induced B field always opposes the change in flux. Faraday's law, if you change the magnetic flux through some kind of a region, you're always going to get an EMF. Now that's important. You're always going to get an EMF. You may not always get a current, like if it's not a conductor, but you'll always get an EMF if you change the magnetic flux through some region. Then we learned about these eddy currents. If you pull this non-magnetic material through a magnet, you're having changing flux, so you're going to get an induced EMF. And since it's a metal, you get an induced current. And that's incredibly important because they use it for magnetic braking. All right, so Faraday, he demonstrated that a changing B field creates an E field. Now so Faraday, he was just an experimenter. He didn't know how to do math much. Maxwell was a theoretical physicist. He was the mathematician. So he wrote the theory of electricity and magnetism. So he just predicted that this should be true. And it turns out it is true. And this is incredibly important because this basically explains light. If you have a charged object and you accelerate it, you get changing E fields, changing B fields, which recreate themselves, and you get a wave. And the wave travels at the speed of light because it's light. All right, it's light. And the important thing about that is every single type of light has the same speed of light, 3 times 10 to the 8th meters per second. But remember, speed of light equals f lambda. So this is constant, but you can have any kind of frequency and wavelength as long as the product equals the speed of light. So, you have really long radio waves, really small gamma rays, and so forth and so on. So you have this spectrum of light. And we talked about how important it is in astronomy. All right, then we talked about the third model of light, the photon model. And again, why do you have to have all these models? Well, because the world demands it, right? There's sometimes that works, then sometimes either of these don't work, so I have to come up with a new one. So photon model of light. Light is made of massless photons. They travel in straight lines at the speed of light. That's in a vacuum. And the energy of a photon, E equals hf. F is the frequency, h is that Planck's constant, that tiny, tiny number. And then you can just use this to solve for f. So you can write in terms of wavelength. Okay, then we did a double slit experiment with super dim light. And these are the single photons that you detect on the screen. So that's the photon model, right? Single photons. But then after you wait a very, very long time, you see interference pattern. Well, an interference pattern means it's a wave. So photons act like particles and waves. That's it. Thank you.